you ever wondered how much water is there in the river or a stream? Hydrologists need this in many situations. Since the volume of water is not constant in any river, the term flow rate or discharge describes the volume of water flowing per second in the stream. There are many direct and indirect methods of measuring this discharge, but today we will discuss area velocity method. To understand the basics of this method, we need to know two things: velocity distribution in the stream and how can we estimate average velocity. How can we estimate the area of cross-section of a stream which is normally of an irregular shape? Let's start. You may have seen water flowing in the stream and saw that the water is moving at different speeds across the width of the river. This is seen here as well. If you see the river, you will find the velocity in the middle is higher and less on the side. If we plot all the velocities, we'll get a velocity profile across the width. Similarly, if we observe the flow of water along the river's depth, velocity is higher at the top and then decreases towards the bottom. The velocity is less at the bottom and the sides because of the friction of the bed and the sides. Friction is dependent upon bed and side material, which can be seen in a cross-section of a river if it is dry. Consider this river reach whose cross-section is visible. We need to find discharge in this river. Discharge, we know, is a volumetric flow rate or volume per second. Therefore, SI unit of discharge is meter cube per second. We can split cubic meters into meters and square meters, which can be further rearranged as velocity units, that is meter per second, and area units, that is square meters. So discharge can be written as velocity into area. We are talking about this cross-sectional area here. We can take care of variation of velocity along the width by dividing the cross-sectional area into sections. Then we can find discharge in each section by multiplying its area with the representative velocity. By adding discharge from all these sections, we will get total discharge. We have also seen velocity variation along depth. However, velocity cannot be measured at all points along depth. In a moderately deep stream, average velocity at 0.2 d, that is 20% depth from top surface, and 0.8 d, that is 80% of depth from top surface, is taken as representative velocity. 0.8 d is chosen because it is closer to bed, where velocity is influenced by bottom friction. Below this depth, silt may interfere, whereas 0.2 d is closer to the surface, where velocity is influenced by surface shear stress and turbulence. For shallow stream, it is sufficient to measure the velocity at one point only to capture the velocity profile, that is at 0.6 d. So average velocity is taken as velocity at 0.6 d. To measure velocity at these points, a current meter is used. Various types of current meters exist in the market. This is a price current meter. It's a vertical axis current meter consisting of wheel with cone-shaped cups attached to it. Cups get filled with water and turn the wheel when placed in the flowing water. The number of rotations and the time period is noted. By calibrating a current meter, we can find stream velocity V at instrument location by using a rating equation that is of the type V is equal to A ns plus B. Ns is rotations per second, A and B are constants of the meter. A weight is normally attached to the bottom of a rod carrying the current meter to stabilize it as shown here. So now we have taken care of vertical velocity distribution and the velocity variation along the width. Let's go back to finding the area of cross-section. We have two questions here. Does adding all these rectangles will give us area of cross-section, or how do we select the width of these rectangles? Let's find the answer to these questions. Draw a cross-section of a river and divide the cross-section into segments with the help of verticals. How do we select this segment's width, which is distance between two verticals. There are some general guidelines for selecting the segment width to minimize the error in measuring discharge. Number 1, segment width should not be greater than 1/15th to 1/20th of the width of the river. Discharge in each segment should be less than 10% of total discharge. The difference in velocity in the adjacent segment should not be greater than 20%. For these reasons, the verticals may not be equally spaced. On these verticals only, the current meter is placed at 0.6D or 0.2D and 0.8D depending upon the depth of the stream. This is shown by the pink circles. Let us make rectangles such that the verticals bisect the rectangles. If we add area of all the rectangles, it should cover the entire cross section. We'll see that the rectangles located in the middle, that is these two, are covering the area of the profile. However, the rectangles at the extreme ends, that is these two, leave some area on the profile. Let's study these more rigorously. We'll mark these verticals as 1, 2, I, and last one n-1. Widths are named as W1, W2 up to Wn, and depths are named as Y1, Y2 to Yn-1. Then we make subsections starting from W2 to Wn-1, which divide each width into two equal parts. Let's find areas which is shown in grey and red. First we'll take this rectangle with the length Y2 and width equal to W2 by 2 plus W3 by 2 and name the vertices of shaded portions. Looking at this part, we can see that this small red triangle's area is approximately equal to that of this black triangle. Therefore, the area of rectangle DEFG is a close approximation to the area of red portion. Area DEFG will be W2 by 2 plus W3 by 2 into Y2. We can write W2 by 2 plus W3 by 2 as W2 bar for simplification, and thus area is W2 bar into Y2. Similarly, we need to find area of triangle ADE. To have uniformity and to make a protocol for calculation, we'll make a rectangle with depth Y1 whose area is equal to area of triangle ADE. Let's say the width of the rectangle whose area is equal to triangle ADE is W1 bar. The area of triangle ADE is half of W1 plus W2 by 2 into Y. We can express Y in terms of W1, W2 and Y1 by using similarity of triangles ABC and ADE. So W1 by Y1 is equal to W1 plus W2 by 2 by Y. The value of Y can be substituted here. So area of the triangle ADE comes out to be square of W1 plus W2 by 2 into Y1 divided by 2W1. If we now compare area of this rectangle with the area of triangle, we'll get W1 bar, which is effective width, as a square of W1 plus W2 by 2 by 2W1. Remember, this is done to make a protocol for calculation only. Let's summarize all formulae. Area of first triangular portion will be W1 bar into Y1, where W1 bar is equal to square of W1 plus W2 by 2 by 2W1. Similarly, for the last triangular section, area will be equal to Wn-1 bar into Yn-1, where Wn-1 bar is equal to square of Wn plus Wn-1 by 2Wn. All the in-between rectangles have an area equal to Wi bar into Yi, where Wi bar is equal to Wi plus 1 by 2, where I varies from 2 to n-2. Let's do one example. We need to find discharge for this data. Here stream profile and current meter locations as well as revolutions with time are given. The calibration equation of the current meter is also given as V is equal to 0.03 N plus 0.05 meters per second, where N is revolution per second. It was used to measure velocity at 0.2 D and 0.8 D as per given data. Let's plot the stream profile from the given data. We'll use the first two columns for this. At 0.8 meter distance, 0.5 meter depth is given. At 1.7 meter distance, 1 meter depth is given. Similarly, we can plot all the verticals. Then we can join the endpoint of these lines to get the profile of stream section. After drawing the verticals, we can find width in between verticals. For example, this one will be 1.7 minus 0.8 equal to 0.9. Likewise, other widths can be found. We can mark locations of velocity measurement for understanding, though this is not going to alter the discharge calculations. For the first vertical, 0.2 D of 0.5 meter will be 0.1 meter and 0.8 D of 0.5 will be 0.4 meter. Let's now calculate area of the sections. To calculate the area of first section, we need to find effective width for the first section. Let's apply the formula which we derived earlier for the first section. That is square of 0.8 plus 0.9 by 2 divided by 2 into 0.8. This will give effective width of 0.977 meter. We'll put this 0.977 meter in the table here, and then we can calculate the effective width of next section, which is a rectangular section. So effective width will be 0.9 by 2 plus 0.9 by 2. Therefore, this will yield 0.9 meters of depth. Similarly, we can calculate the effective width of all the sections. Remember, the last section is the triangular section, which is like the first section. We can calculate the effective width as square of 0.9 plus 1.1 by 2 divided by 2 into 0.9, which gives an effective width of 1.168 meters. Now we can find area of sections, which is equal to depth multiplied by effective width. Area of first section will be 0.5 multiply 0.977, which equals 0.488 square meters. Likewise, we can calculate the area of rest of the sections. Let us now calculate velocity at 0.2 D. Here, rating equation of the current meter is given, which is this. For the first vertical, revolutions are 12 and the time taken is 48 seconds. So revolutions per second will be 12 by 48. Putting the value of N in this equation, we will get velocity equal to 0.058 meters per second. Similarly, we can calculate rest of the velocities by using appropriate N. The average velocity will be half of sum of velocity at 0.2 D and velocity at 0.8 D. For the first vertical, it will be 0.058, and we can repeat the process for the rest of the velocities. Discharge, we know, is the multiplication of the area into velocity. For the first section, we'll multiply 0.488 by 0.058 to get 0.028 cubic meters per second of discharge. Likewise, we can get discharge for all the sections. Adding all these discharge values, we can get total discharge.